All right, I'll go ahead and start. So we do have an exam on Tuesday, right? Because I'm also been notified that we're pretty much almost out of class time, aren't we? Yeah, which is okay. It just came up really fast. Okay. So, for each of the following questions, indicate which data structure would be best suited to handle each scenario. Your choices are array list, linked list, stack queue, tree, priority queue, set, or map. So this is the first batch of questions on this practice exam. This practice exam is, I think, fairly robust. It'll take some time to go through. But this one, this one's pretty good. It is and this is a series of questions that will be, similarly mimicked on the exam itself. Let's just get into it. You need to model which patient should be seen next at a hospital. Patients should be seen in order to in as close to the order of arrival, but patients in a more severe situation should be seen first. So which of these data structures are these? Yep, a priority queue, definitely, 100% a priority queue. Priority queues are all about, hey, somebody is really sick, we should definitely see them first. It's all about being able to cut in line because of some kind of importance. A router needs to hold packets in a buffer and deal with them in the order they appear. Which data structure is that? Stack does not deal with things in the order they appear. Stacks are first in, last out. Yep, queue. Queues deal with things in the order they appear in. So queues. You need to model a hierarchy. So something hierarchical. Yep, trees, definitely trees. You need a data structure to hold your previous decisions in case you need to backtrack. That is a stack, yes. Now, one thing I often would get when I would ask this on an actual exam and leave it open-ended is that I would get the answer recursion. That's not a data structure. Recursion is a technique. Stack is what's used. You use the stack implicitly to do recursion.
Why is it not linked to this?
You could do a linked list, but if you only need to go backwards, then a stack is all you need. A linked list could work. A linked list is correct, but it is not the most correct. All right, answer the following vocabulary questions. The node at the top of the tree is called what? Yep, the root. The links from a node to its successor are called what? We have a lot of terms for them. So the links from a node to the node successor nodes are called what? Whoa. These can be either referred to as branches or as edges, or I guess technically as links too. The predecessor of a node in a tree is called what? It is the parent node. The nodes that have the same parent are what? Two nodes that have the same parent, we call them sibling nodes. So we use a lot of family terminology in this, family tree terminology in this. describe without using code how to calculate the height of a tree recursively. Okay? The height of a tree really depends on the definition we're using. In this class, I use the definition of a tree being. I like. I know that seems a little silly, but it really does depend on which definition you use. Because I have to pull up the whiteboard. Because as it turns out, you've got. I don't want text. Draw. You know. So here's a tree. And this tree would either be described as having a height of 3 or 2. And that depends on what you're counting. So here, if you're counting how many layers of nodes there are, the height's 3. Otherwise, if you're counting the max distance for the max distance in edges from a root to a leaf, that's 2. Now, I personally like the first one we talked about, the node height, because we're looking at a perfect tree here, okay? This tree is perfect. And the definition of a perfect tree is pretty darn useful. It becomes a lot more elegant if you use height correctly. Sorry, if we use height as being the height in nodes. Because if it's the height in nodes, we can just simply say a perfect tree is defined as having 2 to the h minus 1 nodes. Is the height of h. Sorry, a perfect tree is a node. Sorry, a perfect binary tree is a tree that has 2 to the h minus 1 nodes where h is its height. There's literally no other way you can fit it other than being in that shape. Right here it's 2 to the third, 8 minus 1 to get 7. All right, so how do you calculate the height of a tree recursively? Well, the height of the tree is fairly straightforward. If you don't know how big a tree is, just simply by looking at it, which we won't for very large trees. But so the way we calculate it is you've got this, you've got this, you've got this, you've got left and right. Okay, the height of the tree is 2 to the h. Sorry, you've got your left height, you've got your right height, okay, and you take whatever one is greater, okay, so the max of those two, right, choose the max of one of those two, and then add 1 to it for the root. Right? So plus 1 over here, I guess. Right? Choose the max of height of what's to figure out your height recursively, you figure out, okay, I figure out the height of my left tree and my right tree. The bigger one's obviously more relevant here. So that's the bigger one, my tree, and then I have to add 1 for myself. And the other trees can figure that out recursively. Also, it's pretty useful to figure out the height. We can say that, hey, let this be a null node, okay? Let this be null. The height of this is 0, right? So if you've got a tree that we're trying to figure out, hey, what's the height of this, so here, once we get to a leaf, the leaf figures out, it calls its left child and its right child, sees both are null, so they're 0, so he just simply says my height is 1 plus 0, right? So the height of a tree is, recursively is, it's the bigger of its left or right plus 1. I'm sorry, I don't know if it's After Effects or COVID or whatnot, but I have been feeling a bit not as collected in my thoughts as normal. So don't know. It's supposedly something that happens with COVID, but don't know what it is fully. All right, Draw an example of each of these following types of binary trees, using a different example for each possible tree. All right, so we've got full, complete, and perfect. And I used the term, let's go ahead and use a different example for each of these, because if we don't, then some smart Aleck's gonna come along and say, okay, Professor Rosen, I'm done. I've drawn this one for everyone, which doesn't necessarily show me that you understood. Okay. Okay. So let's go ahead and draw some. Okay. So what are some? So let's start with full, because we went over perfect already, right? To the h-1. I'll do that again in just a second, but full is really cool. It's a very interesting definition, which is that every node has to either have two children or two children or no children, right? If you have children, you have both. Otherwise, you only have one child. So it's a zero child. Ugh, no, don't have one child. That's not full. So this is a full tree. Okay, there we go. This tree is full, right? You can see that every node has either two children or one children. We draw some more node over here. Right, still full. But if I add like a single node here, that no longer becomes full, right? If I add another node here, that's not full. If I were to add one over here, it becomes full. Make sense? All right. So full trees, we will actually take a look at them later in this exam. We're gonna write a method on how to check if something is full, if a tree is full, right? So next we need to check out, okay, what is a perfect tree, right? We've said that. 2 to the h-1 nodes. So this is a height of 1. 2 minus 1 is 1. 4 minus 1. 8 minus 1. And then the next one would be, we would add 8 more nodes. That would be 8, it would be 16 minus 1 nodes for a total of 15 nodes. All right, so now complete trees are very similar to perfect, but they're primarily used for when we do heaps. Okay, it must be the, yeah, it's the electric charge. Okay, and now this is just me. Okay. So a complete tree, hold on a second. Okay. Swear, I've never had issues until I came to Japan, and then it's like you cursed my electronics or something. All right, so complete tree is perfect on the top. Completely perfect on the top, okay? And we can see that because I was adding nodes to a perfect tree, right, on top. I drew a perfect tree, and then I started adding nodes to the bottom of it. Okay, and then what we do is that so this area, it was perfect. And then what we do for this one is that for a complete tree is that is that in order to be complete, it has to be filled left to right on the bottom row. No gaps. So this is a complete tree. However, if I remove this and there's a gap, no longer complete. Make sense? Now, why is this? This is because complete trees are primarily used for heaps, and we want to be able to, and everything wants to be easily. For this, we like to have complete trees are great if you want to easily turn everything into an array. 3, 4, 5, 6, 7, 8, 9, 10, where the number corresponds to the index of that node if it were to be embedded in an array, where you can just go left to right and number them, and that would be the index. And then you could use the formula of, twice my height to find my child. Or twice my height plus 1, rather. Twice my height plus 1 and twice my height plus 2 to find my child. Okay. Next. All right, and once again, let me just elaborate a bit further. So adding on 2 nodes over here, this is also complete. But again, if I were to remove any one of these nodes over here, it would no longer be complete. Okay? Complete is not one of those things I would ask you to, I'm going to ask you a question in this, on the during practice exam. Can we check if a tree is full? Given a root of a tree, check if it's full. Checking if a tree is complete, unfair, I think. A bit unfair. Because it's not really something you can check recursively, as you can see, right? This would be, this is actually something that if I were to check it, I would be using some variation of breadth first search. Okay, so now let's go on to another portion of this. All right, so for this one, I have some good multiple choice variations of this that require you not to do some drawing, but basically it's the same thing. In order to answer it, you do need to draw it on your own paper or something like this, but like the answer itself doesn't require you to draw for these kind of questions. Like you don't have to take a photo of what you're drawing is the point. Instead, for these questions, there's something like, hey, which of these does not result in the tree? Which of these sequence of add operations does not result in this tree? If that makes sense. Because every add operation results in a tree because you're going in a certain order. So what we're going to do is I will read this from the bottom, put it on my bottom screen for a second. And what we got to do is that we got to draw the binary tree that forms from inserting the following integers. And actually, so we don't follow along blindly, I have a cunning plan. Please. Paste. There we go. Almost as though it's almost as though I grew up using computers. Seriously, just to clarify, when I was born, I didn't really. That was pretty much when computers became household objects. So in the 90s, there was always a computer in my house that I always had access to, and yes, it ran Windows. And the first one I had didn't even run Windows 3.1. That one ran DOS, and eventually we installed 3.1 on it, and I used that one through high school because I could, and it was because that one was the kind of a computer you didn't need, at that point, the internet wasn't fully developed enough that basically computers became giant internet terminal machines, if that makes sense. Right, you had your set apps, and that was about it, and your games. All right, anyway, enough reminiscing. I can talk about that later. All right, so first item's always going to be the root. Okay, so that will be 42. And the rule is, of course, anything less goes to the left, anything greater goes to the right. Of course, if it's like alphabetical, if it comes alphabetically first, I'll go to the left. If it comes afterwards, it goes to right. No, I'm not going to use alphabets on the test. That would be, it requires too much extra thinking about going A, B, C, D, E, F, G, you know. Seriously, we all have to do it, even the native speakers. Alphabetical order. I know there's some really cool poems and stuff for the Japanese hiragana syllabary, but I'm sure there's equivalent, is the point. All right, so 10 goes to the left. Then we add 50, which would go to the right, because it's bigger, not because it goes left-right, but because it's bigger. Okay, 12, go to the left because, go to the right because it's bigger. Then go to the left because it's smaller. 17, bigger than 42, wait, no. Again, this is what I'm saying. I'm addled. Okay, we did these. 12 goes to the left because it's smaller, goes to the right because it's bigger. There we go. Doesn't seem right. Have I done it wrong every other semester? No. 17 also goes left because it's less than 42, then it goes bigger, bigger, bigger. Okay, 80 is bigger than everything we've seen so far, so every time we insert it, it will go further and further to the right. Negative 12 goes to the left. Smaller than everything else we've seen so far. 100 is bigger than everything else we've seen so far, so it goes here. Then 96 goes all the way to 100. Once it sees 100, it goes, oh, I'm less than 100, so I go to the left. 105 goes all the way to 100, sees 100, goes on bigger, so I'm going to go to the right. 86 goes over here to 100. It's less than 100, goes to the left of 100. Then less of here to 86. And then finally 72. 72 goes here. All right. That looks right, I think. Ugh. Okay. Draw using your previous answer. So the next one, because why make more work for myself? Draw what happens when you remove the following. Now, typically what we'll have for the exam, what I've got some multiple choice questions about, like, here's our initial tree. Here's the items I removed. Please select the one that fits. Now, these are multiple choice. However, please do actual work that, scratch work, and upload that scratch work. Because that way, in case you select it wrong, I can give you partial credit, All right, using your answer, draw what happens when you remove the following. 42. So this is actually so funnily enough, this is an interview question I've seen sometimes. Not how do you delete a node, but how do you find what it would turn out to be the next in order node. Before I forget, I do want to mention there are a few websites that you can that are worth. And I see this on this website, by the way, Pramp. If you're not familiar with it, I don't know why you would be. It's pretty awesome. I would use this to do to learn about peer-to-peer. Sorry, part of the issue of going in for interviews at tech companies is that it's difficult. Is that it's like scary to do so. You're like, oh God, am I good at enough or not? And like, oh God, I'm going to go and I'm going to completely flub because it's going to be my first time. Don't let it be your first time. Instead, sign up for a website like this called Pramp. What it does is that this is peer-to-peer mock interviews. So they provide you with a question, they provide them with a question. like you were given a question to use as your interview question on somebody else. You act as the interviewer for somebody else for half an hour. They act as the interviewer for you for half an hour. And you're given, and here's like, again, this question that I kept having to ask people. In a binary search tree, the in-order successor of a node is defined as the node with the smallest key greater than the key of the input node. Given a node, asked to write a function. And you're allowed to work in any language, any of these kind of languages over here that are supported. And this is a very basic question, in my opinion, because all it is go one to the left all the way to the right. That's all you have to do. Why am I bringing this up? Because that's what this problem is, to remove an item, right? To delete nodes from trees, we have three cases, okay? We have three cases of deletion, okay? One, the node we want to delete is a leaf, right? Right? There's our root, right? There's the trees and its subtrees, and here's the node we want to delete. To delete this node, all we have to do is just replace it with null. Okay? That's case one. Case two. Actually, I'll make it all twisted to make it more interesting. Case two. I have the node I'm trying to delete has a left or right subtree. It has one child. In which case, you tell your grandparent that it's going to need to adopt the child. So you basically return your descendant, your single descendant, and during the relate method to say, hey, replace me with replace it with the child. It gets, now on the other hand, if you are trying to delete this node and it has two subtrees, or two children, that's where it gets messy. And what you do for that is that you find the next in order predecessor. The next in order predecessor. In the interview question we were looking at, I was looking at, it said next in order successor, which is the smallest node greater. That's one to the right, all the way to the left. In other words, yep. One to the right, all the way to the left of 9 would be 11. That's correct. So that's the next in order successor. But for deleting, I like to do the next in order predecessor, which is the node in this subtree, which is the biggest. In other words, the biggest item that is smaller than me. Okay, how do I find that? Well, if it's the biggest item that's smaller than me, all the items smaller than me are one to the left, and then the biggest item in that would be the one that's all the way to the right of that. So now using that, okay, I haven't described what to do once we get there, but let's go ahead and now see what happens when we do get there. So 42 says what we need to do is that we need to delete it. We need to go one to the left and go all the way to the right, which gets us to 17. So now what do? We take, the reason we do this is that once we find 17, we can move 17 to the root. We can replace the root with what was there. Why? Why do we do it like this? Because this doesn't require you to change anything in the tree. By using the next in order predecessor, everything to the left of 17 is still going to be smaller than 17, and everything to the right of 17 is going to still be greater than. Right? That's it. The reason we're choosing the biggest item in the smaller tree, in the smaller side, is that since it's the biggest item in the smaller side, everything can go to the left of it. And yet everything is still going to go to the right of it in this tree. Okay, so now that we've done that, we now instead delete this item over here. And deleting the item that you found is always easier because it's only ever going to have one node. This is either going to have either one child or 0 children. Never going to have 2. If it had 2, that meant it had a right node, which means you could have, there was something bigger to it, so you would have gone to the right. So always easier. Okay, next it says to delete 12. 12 is very simple to delete. Delete 17 again. So we go one to the left, and we go all the way to the right. And all the way to the right just happens to be nowhere, so we're going to just, so it turns out to be 10. And again, if we look at this, yeah, that makes sense, putting 10 here. And then finally deleting 96. So we find 96. 96 has one child. So what we do to delete 96 is that we just simply have 100 adopt 96 child. All right. Which of the following is a pre-order traversal of a trees left and right? Now, we learned about going back to the whiteboard, traversals of trees. We learned about 3 of them. There are 4 of them that you have to concern with. We've only learned 3, but you don't have to worry about that 4th one on this test. Okay, we've learned pre-order, in order, and post order. There's also, and these are all recursive, which is why we learned them right now. Okay, and it's also why we don't learn the other one, which is level order, which is just another fancy way of saying breadth first search. That's why we didn't learn it, because we learn it later as breadth first search. And what that means is that, again, it's the way I was numbering the nodes in when I was doing the complete tree. It's going left to right from top to bottom. Natural kind of reading order. Okay, so these ways, you always process, so for level, pre-order, in-order, post-order, doesn't matter what it is, you always recur on the, it's always you do X order on root dot left and X order where X is whatever, it's either pre, post, or in, root dot right. Okay, you call it recursively, and it's always going to be left before right. So the difference between pre, or in, and post is where do we put the root node? You know, do we process root here, or here, or here? Well, the easy way to remember, if it's even, and yes, it requires some knowledge of English prefixes, okay, but it's easy to remember if you remember your English prefixes. If it comes before, right, if it comes before, if processing the root comes before the your recursive calls, then it's pre-ordering. And that means that basically we'll handle the roots first. We'll always handle the root first. If it's in between your recursive calls, it's in order. And if it's after your recursive calls, it's post order. Okay. Okay, so going back, that means that for this one, that for pre-order, it's root, process the left tree, process the right tree. Root, left subtree, right subtree. For post-order, it is handle the left, then the right, then the root. Okay. All right. Give me a couple seconds. I'll be right back. All right. So continuing on, we've got min heap that forms after inserting the following integers. Okay, draw a min heap. So min heaps are, again, created differently than arrays are. So we'll go ahead and copy this. Paste it over here. Okay. To do a min heap, we need to, so heaps always follow the same rule, which is you add it into a location so that it will be a complete tree. Okay. When you're adding into a heap, it's always added into the next position for a complete tree. Not so you don't handle it like going left to right like you do with a regular binary tree. And then after you insert your node into its location, its complete tree location, that's when you have to reorder it. And the way I like to think about it is that the lighter items bubble to the top and the heavier items sink down. It's the easiest way to remember it. Okay, so 8. So then we add this at the so then we add 10 to the next location, which is to the left, and then 50 gets added to the next location, to the right. Make sense so far? Because again, because this is the next location for a complete tree. You go left to left to right, and then when you get to the end of a row, you start another row. 50. 20, nothing exciting happening yet until we get here, because all the items we've inserted have always been heavier. Now we add a 1, okay? And what we have to do now that we've added a 1 is that we have to let that bubble to the top. And the way that works is that you just, whenever you insert anything, including these heavier items, all you have to do is you're asking, is this child heavier than its parent? If it is, swap. Okay, is this child heavier than its parent? Yes, it is, so swap. And you just keep doing that until you can't swap anymore. 4. 4 is lighter than 50, so 50 sinks down. 4, 50, and then 4 can't bubble up to the top any further, and then we add 3. 3 is lighter than 4, so it bubbles up. And there you go. And notice that this doesn't look anything like a tree in terms of, anything like a binary search tree. It's certainly a binary tree, but it's not a binary search tree. Okay. Now, drawing the heap you drew above, draw the heap after removing an element twice. So we're only ever going to consider deleting the minimum item from the tree. Okay, so delete the minimum item from a tree. What we do is that we have to make sure it maintains its complete property at all time, which means what we do is that we delete the top item, and we move the last item in the tree, in the heap, to the top. Then we figure out, okay, how do I fix this? And the answer is you swap with your lightest child. Well, 4 and 3, sorry, if you need to swap, which we do in this, which we usually do. 4 and 3, well, 4 is heavier than 3, so it should sink down. And it can't swap with 8 because that just doesn't make sense. Okay, we'll see that what I mean by that in a second. So here, it says we're going to delete twice. So now we're going to delete the next minimum item, which is 3, which means that we need to put 50 up here. Now 50 is heavier than both of the children, but in order for this to stay correct, what we need to do is that we swap with the lighter child. And there we go. Huffman coding. So I didn't get the chance really to talk about some of my hobbies and stuff and the like, but Huffman coding is pretty cool. There's 2 types of compression in our world. Okay, the first is lossy compression, and we see that everywhere. From any time you pull up a YouTube video or listen to what used to be MP3 files, but are now more advanced codecs, compression, decompression algorithms. These are algorithms where they're like, those little monkey brains can't reproduce everything anyway, so why should we bother either? So, and that's there's truth to that. Like, if we throw out some color information, that's okay sometimes. If we throw out some audio information, that's okay sometimes. You can't always hear it, and you can't always see it. It's why it's why different, like if you're into the whole piracy scene, why you have different competition between different piracy groups on releasing pirated movies based off of how good their rips are. What the quality of the rip is, and file size versus quality. It's an eternal argument there. There are some exciting codecs that have been out. VP9, AV1. Those are released by different companies, and it's pretty awesome to see how good compression has become. And I mean, like, it's good enough that it was. It doesn't sound exciting, but I mean, it was exciting enough to be an entire HBO series, Silicon Valley. The entire plot point, besides the human drama, is that they've developed a compression algorithm that is far superior to everything else. But anyway, that is lossy compression. Lossy in general is what I mean about talking. Or rather, I forget about Silicon Valley's algorithm, but what I've been talking about primarily is lossy compression. Going if you zip up your Word document or your code, you don't want to lose any data. You don't want the computer to throw any out and go, it's going to be fine without the E's in there. You don't want that to happen. Instead, what you need is you need lossless compression. Now, there are lossless audio codecs out there, like the .wav format, the oldest format there, that's lossless. Same with FLAC, free audio, lossless audio codec, which is a compressed form of WAV. And those can really, and using FLAC over WAV files is, that can really save space. But for text, Huffman coding is kind of as optimal as it gets. The idea here, though, is that the trade-off cost, what's the cost of compressing? We have to send the Huffman tree along with it, which is basically the instructions on how to compress it, how to do this compression. Also, I don't know how well it works for Asian languages, because this assumes a very Anglo-centric language, which is that we have an alphabet that has like 26-ish symbols in it. 128 if we were using ANSI, but that pales in comparison to, again, like the 2000-ish official Japanese kanji, right? Yeah, that's about as many? No? No, I'm saying official, the ones that are like, okay, this is the ones that you should understand. I know there's like 20,000 of them. I know there's 20,000 of them, but like there's like a official list, I think, or something. I don't know if it's for like the exams or whatnot, or high school. It's just something that's a. Give me 1 sec. Okay, I want to. I now want to know. Okay. History. All right. There are nearly 3,000 kanji used in Japanese names in common communication. Okay, 3,000 common kanji. There we go. That's more of what I'm talking about. Not official. But then again, also you have your entire, then plus add on to that your only, 40-ish, 50-ish hiragana, and then 50-ish katakana, only, so again, the point being is that this scheme might need some, there might be a more optimal way for Asian languages. I don't know. I know this is an optimal way of compressing, but I mean, like, again, the tree you're going to get for this in Asian languages is going to be less than useful, unless you do some stuff, some manipulating stuff. Regardless, still cool algorithm. And what it does is that it takes advantage of the fact that, hopefully you watched the videos on this, but if you didn't, this algorithm takes advantage of the fact that basically that when we're talking about ANSI and Unicode, or specifically ANSI, which is the way that we compress English letters, or encode English letters in normal like communications, is that like everything has like every letter gets a number associated with it of 8 bits. Technically 7 bits, but like, so here 97 is, so A would be 1, it's 97, so what's the biggest power of 2? 60, so 64 plus 32 gives us 96. So 16, 8 plus 4 plus 2 plus 1. Okay, so there you go. That's the encoding for A, I believe. I believe A is not, lowercase a is, I believe lowercase a is 97. Okay, which, and that would it be 11000001. Okay, and the idea here is that this.
Like all the zeros has to be 0, like.
Well, this is not if we're not using. Well, the idea here is that like everything takes up the same amount of space because we're assigning every symbol as kind of the same. We need a common form of communication. Okay, and so you need to understand if you get this bit this byte, then this byte means A, and then this byte means B. Okay, you need to know what those bytes are. Okay. But this, this worked for a while until, the internet meant that everybody was communicating to everybody else, which meant that the 256 limit here did not work. So that's why we use something called these days called Utf-8 and Unicode, which is why I can, when I go and look up kanji, I can take this and literally copy it and paste it, and because they're all characters, they're all Unicode characters now, and they're all encoded properly. But regardless, the way Huffman encoding works goes, well, we've given everything kind of an equal length, but if we want to save space, then what we need to do is that we need to make everything not an equal length. But we're going to be using a different, and also every document has a different kind of frequency of characters, so we need to be able to adjust for that, right? English is going to have, things in English are going to have a different frequency of characters than Spanish, which is different than French, which is different than German, so those are all going to have different frequencies of characters, going to need different compression. And that's not to, and then also that doesn't even account for the trolls. For instance, the people who do stuff like this, write things like the novel Gadsby, 1939 novel, which does not include any words containing the letter E. The entire book written without using the letter E once. Because, they had no internet in 1939, or TV, so this is how they had to amuse themselves with weird. Yeah, the 5,000. Yeah, I guess. Yeah, and also he can't get away from using his name there. But he says that his primary difficulty was avoiding words that ended in ed, so he had to use did walk instead of walked, so stuff like that. All right, so how do we construct this? Well, the first thing you do is that you construct a frequency table. You read a document and you say, okay, here's all the letters and here's how often they appear. Okay, so I've already done that part for you. I'm not going to make you do that part. Okay, I'm always going to do that part for you. Here's all the letters. Here's how frequently they appear. And apparently, this document's very weird because it has the letter X once. It has A, P, L, E happening 50, 40, 20, 60, and times respectively. So we want to draw the Huffman tree for the symbol. To do so, we use a priority queue. Okay. So what we do is that we arrange the letters in terms of frequency. So we let each of these be a node. Each of the letters is a node. And we arrange this again in order of least to greatest. So min heap, in other words. Go ahead and be a bit more. My handwriting's terrible right now. So 20L, P is 40, A is 50, E is 60. Okay, and now what do we do? So the way the algorithm works is very simple. Take the two first things in the queue, remove them, and combine them into one supernode. How do you do that? You take you take what's on the left and what's on the right. So you take the first thing and the second thing, and they become the left and right respectively. So X and L, they had a weight of 1 and 20, and they combine into a new node of height 21. Moving that over there. And now what we do is that we take this X and L, the single node, and we insert it back into the priority queue. But this is a priority queue. So it skips this way to the front. Now we do the same thing. We delete the left side, we delete the first thing and the second thing in the queue, which is XL and P. P goes on the right, XL goes on the left, because they were the second and first things. Then they combine into a supernode. The combined weight of 61, because 21 plus 40 is still 61. I've still got it. I still know how to do grade school arithmetic. Awesome me. Okay, and now we put X LP here, and notice that its weight is somehow just slightly bigger. It's almost as though I constructed this problem to deliberately do this or something. Next, we have A and E. So A and E. Yeah, it was terrible. A and E, those got DQ'd. Okay, and what we're going to do is that we are going to take them and we're going to combine them into a node that has a combined weight of 110. We're going to then lasso these guys and drag them down again. And redraw this because it looked terrible. Okay, and then finally, there's only two things left here, so reinsert A and E, right? Because the order is important, right? We reinsert A and E, there's two things left, we DQ both of them, and we add them into one node that has a combined weight of 171. The overall weight isn't important. It's just what's important is the structure of the trees we get, which is as follows. X, L, P, A, E. And so now what we do is we also label each of the edges for the next part. We can also label the edges for the next part. Anything to the left would be a 0. Anything to the right is 1. And now we have a way of communicating, and now we have basically a code for decryption. We have the zeros. We say, okay, 3 zeros in a row, that's an X. A 0, and then a 0, and then a 1, that's an L. A 0, 1's a P, a 1, 0 is an A, and a 1, 1 is an E. And it always confused me how in the world did this work, but it does work because because you reset each time you finish reading a character. But to encode, it's not too bad. So to encode Apple, you always start at the top. So we would go 1, 0. So for Apple, we would go 1, then we'd go 0. So 1, 0. Then P, 0, 1. Another P, which is 0, 1. So A, P, P, and then L is 0, 0, 1. And then E is encoded as 1, 1. And so that's Huffman encoding. And the end result is that things that are twice as, basically things that, the idea behind Huffman encoding is that hopefully with enough characters that occur half as often take twice as long to encode. Sorry, take 1 bit more to encode. All right. Now, talking about coding, do any of you need a break before we talk about coding? You wouldn't mind? Okay. Can take a few minutes. All right, coding, size of the tree. So first things first, let's go ahead and create a first things first, I'll go ahead and create a class that I can use. So I'll create a new Java class, exam2, because I don't actually need to create a new project. And what class I do need to create, oh my, sorry, is just simply a private static class. I just need to create the node, private static class, node. Okay, and because that's all I need to do in order to get this to just simply compile correctly, I need to use and you know what? I'll do a node that takes an E, extends, comparable E. I don't even know if I need that much, but hey, whatever. Node E left, node E right. It just feels better to do it like this. And then finally a node, sorry, not node, a E item. Right, because the only class that we'd be using in a tree would be the root. So the only instance variable we care about is root. And all the methods require us to pass in the root of a tree or binary tree. So it doesn't really matter that we don't have a true node class here. Now the first method that we asked ourselves to do is write a method which, here we go, write a method which, given the tree, the root of a tree or binary search tree, tells us how it computes the number of, and let's see, here we go, number of nodes in the tree. You can use the size method. Forget that it existed to begin with, right? And then over here, what we have, oh, okay, so okay, right. I didn't use comparable because we don't need it for any of these. Okay, node E, we don't need comparable for any of these. All right, so size of tree, let's go ahead and just simply quash the error by returning -1. Obviously, there's no tree of size -1. So, but we need to start by establishing a base case. Base case new. So base case, we should always, with trees, we should always consider, you know, how does null affect everything? So in this case, we're just passing in so we either have a null root or we don't have a null root. So if it's null, then we would just simply return 0. If root equals null, return 0. If we're not null, there's not really much else we can tell, right? If we're not null, then this node over here has a left subtree of indeterminate size. It could be null, it could not, it might not, but if it's null, no problem. And then we have a right subtree of indeterminate size. So, and we're asking how many nodes are there total? We've only got one definitive answer, which is that this guy, he's one node, right? Me, the root. If I'm not null, I'm at least 1. And then I got to figure out those two, the size of those two things, right? And what are the size of those two things? Well, if only I had a method to figure out how big they were. Well, I have a method, it's called sizeTree, so we're going to use that. So, I'll write this long at first. So int my size is equal to 1. Int left size is equal to the size of the tree on my left side. right? Root dot left and int right size is equal to size tree root dot right. So I figure out my own size, I figure out my left size, and I figure out what my right size is. And then my total size, the total size of this tree is equal to my size plus the left size plus the right size, right? Make sense? And if I really wanted to, I could just do this as one line, right? Where it'd be 1 plus the size of the left side of the tree plus the right side of the tree. This is, I think, an easier question than I would ask on the exam. But the next questions would be harder than what I would ask on the exam. But this one's fairly straightforward because, well, again, the entire idea here is that we're testing recursion. And this works because, again, because basically we're just using recursion to be lazy. All of my children, right? If my children are null, they'll be 0. That's easy enough. But if I actually do have a child, then he figures out his own size, which will require his children figuring out their own size, which will cascade until they hit nulls, and then they'll return 1, right? They'll return 1 for themselves to their parents, who will take the 1s, and they'll start percolating all the way up. They'll start accumulating. Does that make sense or no? Or are people having trouble following along? All right. So let's run through how this algorithm will work in practice. Okay. In practice, the way this works is that we've got 1, all right, so we're over here, and the way we did it is we calculated size left plus size right. So we're going to go to the left first. So I'm not null, so I need to calculate the size of my left subtree, and then the right size of my right subtree. So now we recursively call it over onto here, which says, hey, I'm not null. I'm going to call my left subtree and my right subtree. I'll do my left subtree first. This guy says, I'm not null. I need to figure out the size of my left subtree and the size of my right subtree. And it turns out, because those are null, those are 0. So my result is 1 for my size plus 0, so I return 1. Okay, so this node, we're back at, so finished calling its left subtree. So now it's calling its right subtree. Its right subtree says, okay, I need to call my own left subtree, which calls its left and right, figures out, oh, that's got to be a 1. Those are 0s, so I pass back just a 1. Same over here. He figures out just a 1. And so this node finished calculating its left subtree, its right subtree, so it's my size, 1, plus the left and the right to pass back 3. So this figured this out. It's got 1 plus 3, and then 1 for itself. So it passes back 5. So this figured out, okay, I have 5 nodes on my left side. Do you need me to go through the right side or no? Okay. So yeah, it would go 2 on, it would say 2 on the right, and then we'd do 5 plus 2 is plus 1 for a grand total of 8. Okay. Next one. Write a method given a tree returns whether or not the tree is full. It's slightly different than any of the recursion traversals we've tried so far because unlike the traversal methods, we do care about our children. in order to return what we need to return. Okay. I'll go ahead and call this root instead of tree. Okay, so I want to figure out whether or not this is full. Okay, so my base case here isn't, so first off, let's go ahead and check if root is null, if I don't have any children, right? If I'm null, I'm going to say it's true because I have 0 children, right? But then we got to figure out our other easy base cases. What are easy to figure out? Okay, so first off, if root dot left, we'll go ahead and do this as an else if so that we'll just maybe nice and symmetrical. So if root dot left equals null, if I don't have any children, I'll go ahead and check. Normally I don't check, but if I can say, hey, if my left subtree is null and my right subtree is null, if I don't have a left or right child, return true. It's a full subtree. And then there's 3 other combinations for this, right? Which is that, I've got 3 other combinations, which is if my left is not null, but my right is null, and then what if they're both null? Right? And so in these cases, if we have one child to the left and one to the right, that's enough for us to return false. So if we only have one child, it's false. But now if our left subtree and our right subtree are both not null, well, let's go ahead and instead turn this into an else case, so that, because that's what it has to be in this case. Else, then what? Well, if I've got 2 children, that's great. I'm full as a node, but my left subtree itself may not be full, and my right subtree may not be full. So I would have to return, so now I would have to check, and I'll just go ahead and do this as one function call. Is full root dot left and is full root dot right. So I would ask, is my left subtree full? Is my right subtree full? Make sense? If those are full, then I can safely return that the entire tree is full. So it turns out it's a recursive property, Because you're not going to be, if your left subtree or right subtree is full, then the entire thing can't be full. It's hard for the entire thing to be full. Okay, extra practice. Boolean equals. Check if 2 trees are equals. And what do I mean by they're equal? I mean that they don't just have the same items, but they have the same items in the same location. Give me a second. I'm going to just quash this error before, right, and now I need to put an E there. Okay. Example time. So to check for 2 to be equal, right, what I'm trying to say is that is equal should return true for these two trees over here, right? Where they're 2 as the root and 1 and 3 are the subchildren. But it will not return true for something like this. 2, let's see. Three, 2, 3, 2, 1. Because they don't have the same structure. The items are the same, the structure is different. Now, if we were just cared about the items, the easiest way to check that, because if we wanted this to be true, you know, the easiest way to check that is to do a in-order traversal, because then the items will show up in the same order. Assuming it's a binary search tree. And not just like some tree where you can throw anything in any order, in which case it becomes a bit more complicated. Okay, but to check if 2 trees are in the same configuration, well, let's again look at base cases. So if I'll call them, and again I'm going to change their names to root A and root B. If root A is, so what if both are null? That seems like a pretty good base case, right? If root A equals null and root B equals null, you know, I'd consider that equal, because they're both null, they're both the same exact thing, right? Okay, else if, and now we need to do, and now we'll do similar to what we did over in, for the other problem, which is, we'll copy this, and we'll adapt it for the other configurations, right, the other possibilities. Right, which is, oops, one exists, the other one exists, and they both, and then the else will be both are not null. All right, so these likewise are very symmetric to the other one, right? Here, if the root, if one side exists, if tree A exists but tree B doesn't, or tree B exists but tree A doesn't, then they can't be equal, because something and nothing, they aren't the same. Okay, now if here we've got this other else, we need to check now something new. If root A dot equals, sorry, specifically, if the item is equal to root B dot item, right? If the if they now hold the same, so now that we've established that both sides exist, then we have to check the to see if their items are the same. If they're not the same, return false, right? In fact, what we could do is that we could put in, we can shorten this, return false outside, on the outside, and then have this as an else if the two items are equal to each other. And now that becomes a lot cleaner. So now if the two items exist and they're equal, sorry, if the two exist and they're equal to each other, then we need essentially to check. If that's the case, then basically what we've got is we've got, tree A, we've got tree B, and they both have some subtree, like this. And so what we need to do is check if, are those equal to each other, and are those equal to each other, right? Gotta check if those are equal to each other. And if they are, then the whole tree is equal to each other. So, so just like the other time, we're going to do returns in an AND statement, but instead we're going to do return equals root A dot left, root B dot left, compare the left to left, and equals root B dot right, root A dot right, root B dot right. So there's the recursion for that, right? If the contents are equal of the node of the two roots, check if both the subtrees are equal recursively. Okay. Plenty of time for the next one. Okay. Write a method which returns what characters occur in a string and how many times each occurs. So this is a map question, right? Where we're counting them. In other words, we're doing a frequency count. And this should be fairly familiar to you after watching all the map stuff. Frequency, this normally goes very well for every student, which is, hey, let's go ahead and count these arbitrary things. So first thing we do is that I'm going to create this map of characters. Map is equal to new hash map. And then I'm going to return that map when I'm done with it. So I don't forget, and I don't get any errors. So now for car C, for every character C in, and I wish I could do this in Java, but I can't. Instead, what I have to do is to character array to do a for each loop. Or you can just go for in I is equal to 0, blah, 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 and then use car at I. Either way works. But here what we're doing is that we're saying, hey, for each character, if C so we're going to look at this a few interesting ways. If mat dot contains key C, if we've seen it before, right, then what we do is that we say we should basically get the int previous number of times we've seen it is equal to map.get C, right? Get the number of times I got it, and then say map.put. Okay, now I've seen this character one more time. It's an integer, so I have to update that integer. So it should be, I've seen it one more time, previous plus 1. Okay? And then else else I haven't seen it before, so I say map.put C and 1 there. And this is completely valid as a solution and works 100%. Okay? But I feel like we can make it a bit better, first off. Or sorry, not necessarily a bit better, because this is nice because it's nice and readable. We could also do this. Instead of doing this, instead of having a previous, we could just do that. You know, we could just have a method call inside a method call. But it looks messy and that's harder to read. But let's suppose but it's a real drag to have to ask if we've seen that. Okay? Instead, what if I could just, instead, why don't I, and I always have to just simply put something in one more than the times I've seen it. So can we do that better? Well, fortunately in Java, it does have a bunch of useful abilities. Specifically, if you type in get, you may have stumbled across this one. Get or default. Given a key and a 0. And what that does is that get or default does is that it doesn't take in one character, it takes in two. It says, first it takes in a key like normal, and then it takes in a default value. Normally, if you try to get something that doesn't exist, what happens? It crashes with a key error. Here, no key error. If the key you use would give you a key error, instead you would get the default value back. Here I'm saying 0. So what I'm saying is, now I'll say int prev, for previous number of times I've seen it, prev, is equal to map dot get or default c 0. And what this does is that it says get the previous number of times I've seen it. If it's in there, the previous number of times is the number of times I've seen it so far. It's what's ever stored in there. And if I haven't seen it, the number of times I've seen it is going to be this default value of 0, which makes sense, right? So it gets me, so if I've seen it before, great. If I haven't seen it before, also great. And then I just do map.put again. Map.put, C, and then previous plus 1. And now I don't have to have an if statement to update that. I don't need an if statement for this. I just let the computer figure it out by not crashing. Okay. This one, I've always not liked it because it was far-fetched and write a method which, given an array of integers, categorizes them into numbers divisible by 2, 3, and 5. I really should have given it as like two arrays, which is like an array of things and the array of things you want and what multiples you want it divisible by. But here, example input, write 2. We keep track of all the multiples of 2. We keep track of all the multiples of 3 and all the multiples of 5. Okay, and this was just simply to give people practice on categorizing. So we'll go ahead and do that. And the reason why I never liked this is because I can just simply, is that when I've got this array of items, when I create this map over here, I don't really have to do much. Map is equal to new hash map, and then return that map, and then I know what my categories are, so it's going to be map.put to new array, to new array list. And then map.put for 3 and 5 to each have their own array lists now. And that's it. Basically, I populate with empty ones. If I if I instead passed in 2, 3, and 5 in a second array, suddenly the problem becomes a lot more interesting. Now, and I only had this idea as I was reading it out to you. That becomes a much more interesting problem because guess what? now instead of just hard coding it in, you have to do a for loop. But it's a very simple for loop, but it's still for loop. Anyway, so now we've hard coded those 2, 3, and 5s in. For int number in the array, super easy to do. Map.get. I guess actually. So it's just going to be 3 if statements, I guess. So if number mod, if number is divisible by 2, if number divisible by 2 is equal to 0, then map.get 2.add number. And you can see how unenthused I am by this problem, that I really would, and now I just change it to 3 and 5. Okay? So let's scratch that. Let's go ahead and do it the way that I think is more interesting, which is in array, instead of taking an array, just an array here, we're going to take in int, we'll take in the divisors as well. Int divs. And now, so instead of 2, 3, and 5 being assumed, they're going to be passed in as well. Make sense to everybody? So to do that, what I love about it is that even though it seems harder, it shortens the code up immensely. Because all I have to do now is say for int divisor in divs. Sorry, suddenly transitioned to Python there. Map.put divisor new array list, and boom, just like that. So now I've added as many as those divisors as I want, and then over here for every number, and then I do another a loop on the divisors. For int divisor in divs, if number is divisible by the divisor, then right equals 0. Map.get the divisor and .add to get the number, the list associated with that divisor, add the number to it. We don't need to even put it back in because it's a list, it's stored there. We're just simply getting the memory location of that list that's been stored in there already and adding our item to it. And yes, I find this way more easy and straightforward to do because I don't have to hard code something. Okay, finally, analysis questions. What are collisions in hash tables? Why do they occur? And how are they handled? Collisions in hash tables. Okay. The entire point of a hash table is that we're trying to get this amazing lookup time for various keys that we're trying to store. We're trying to take a key and take it, and we're going to go ahead and store it in an index somewhere in this array so we can retrieve it in constant time. The issue is that the universe of known keys is much, 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 much bigger than your array size, right? Right, the number of keys the universe of possible keys, is much bigger than the size of any array you could store in the computer, because this is infinite. There we go. It's infinite, and your memory is not. Okay? So, y'all remember the pigeonhole principle? Did you learn the pigeonhole principle from statistics? In case you did not, basically there's a pigeonhole, there's something in probstat and combinatorics. It's called the pigeonhole principle. It's a very simple thing, which basically says, hey, you've got a bunch of pigeons, you've got a bunch of pigeonholes they've got to fit into. If you have more pigeons than pigeonholes, then two pigeons are gonna have to share a hole. In other words, if you've got X containers and Y items, and you've got more items than you do containers, then one of those containers is gonna have more than one item at least one of those containers. Same thing over here. So we're going to eventually get collisions. And a collision happens when basically we take a key, okay, and we throw it into a hash function. And that will direct that to somewhere in this table. And suppose we have a key 2, we also direct it into the hash function, and that's going to direct it if it gets to somewhere else in the hash table. And if that somewhere else happens to be the same place as we are, that's a collision. Basically, two items try to occupy the same, two keys try to get assigned to the same index, or try to occupy the same index. Okay, how do we resolve this? There are two ways to resolve this that we've learned of. There's plenty of ways to resolve it, but two ways we learned are open addressing, and the other way we learned about it is chaining, which is extremely popular. Open addressing works as follows. If you get assigned to this space and this space is already occupied, then what do? You look for the next available space. That's open addressing. You look for the next available space. However, that's taken too. Guess what? You still look for the next available space. Now, what comes interesting is that this is called linear probing, where we're looking for the next available space, where next is defined by literally the next one over. But you don't have to define next that way. Instead of looking one away from your original spot, then two away, then three away, then four away, instead you could do something more dramatic, like look one away, one four away, look 9 away, look 16 away. And that's called quadratic probing. And this is useful because it prevents lumping. It prevents big clusters of items from joining in the same place. Okay. The other way of doing it, of resolving collisions, is by chaining, which says, you got a collision, that's no problem, because these slots for a single item, they're not slots for a single item. Instead, every slot is a linked list. And so if you need to go on, you just add yourself to the end of the linked list. And you're like, but Professor Rosen, now how does this still maintain constant time? Lookup. Well, what we do is that we enforce that. First off, we assume that basically these are going to be evenly distributed. That all the keys are going to be evenly distributed across our space, and then we enforce that the linked lists can only get so long, like some constant number, thus making it a constant. All right. What is the worst case runtime of insertion and deletion algorithms in a binary search tree, and why? So, binary search tree, worst case runtime and deletion are O of n for a binary search tree without any other qualifications. If we were to say it was a balanced binary search tree, balanced, right? If it was balanced, well, the average case for all binary search trees is log n. But for a balanced binary search tree, it's going to be log n as well. Because if it's balanced, then you can assure that you're going ensure you can go that you're cutting out half of the items in one go, each step of the way. What does balanced mean anyway? I've never actually defined it, so let's go ahead and define that. For a tree to be balanced, that means that heights it means two things. So let me actually give myself some more space. Balanced means two things. One, heights of subtrees differ by no more than 1, right? So for something to be balanced, it's the heights of the subtrees differ by no more than 1. Okay? This means that basically it takes roughly the same amount of time to go left and right. Okay? 2, which is the important one, which is also important, the subtrees are balanced. Those are the two requirements for a tree to be balanced. The heights differ by no more than 1, and the subtrees are also balanced. In other words, each subtree, their subtree's heights differ by no more than 1. Okay. But regardless, if you maintain this, the heights of your subtrees differ by no more than 1, this ensures that you'll get logarithmic runtime. Okay? And the way self-balancing binary search trees work is that after you do an add method or a delete method, which takes log of n because it was balanced when you added, okay? Well, the way balanced binary search trees work is assume it's balanced when you add something or delete something, and then adding something or deleting something might cause it to become unbalanced. In which case, you rebalance it, which takes log n time. So that will enable you to, and by doing so, that means, and once you rebalance it, then you're rebalancing it so your heights of your subtrees differ by no more than 1 again. Okay. Okay, so anyway, but we talked about what is the worst case runtime for a regular binary search tree, and we just said that that is O of n, and now it's asking why. Well, because,
Just like race.
yep, so let's use a famous English sentence. The quick brown fox jumped over the lazy, and then there you go. The English sentence, the quick brown fox jumped over the lazy dog. It's English. It's one of those typographical sentences because it contains every single letter in the English alphabet. But notice that this tree is severely unbalanced. If I were to ask if the word jumped exists in this tree, I'd start at the. Okay. I'd be starting at the, and then I'd go to quick, and then I'd go to brown, and then I'd go to the right, and then each time I move, what's going on? Well, for a tree, we want to be deleting half of our possibilities. This basically just gets rid of one word each time I move because it's so unbalanced. It's a linked list with extra steps. Or if we just want to be more explicit about it, we can draw that. Here's a severely unbalanced tree. Come on. 1, 2, 3, 4, 5, 6, 7, 8. Right, there's a severely unbalanced tree. And that would take O of n time to find anything. It's just a linked list with extra steps. Okay. So that is all the questions on the practice exam.